Physics 2, Lab 2 by Caroline Miley. So to introduce this lab, we're basically doing the same procedures that we did in Lab 1, and we're using the U-tape method to create charged tapes. Both my tapes actually ended up being negative for me, and I observed that they repelled each other. Some assumptions that we'll be making are that each tape has approximately the same charge spread evenly along the length of the tape, which allows us to treat the tape as sort of a rod or a line of point charges rather than just one point charge. The tape also floats in a straight line, so we're assuming that has no curvature, so we don't have to account for that, and we can just keep the point charges in a straight line like a rod. We're going to be using Coulomb's law, superposition principle, electric force equation, and the principle of static equilibrium. And in my findings, I found that the use of my different calculations differed by a factor of 10 between Lab 1 and Lab 2. How to find the electric force? We're going to use the process of calculating the electric field for each smaller charge, or in this case dq, in the tape, and add it up to get a net electric field, which we'll do iteratively in my code. So we plug in this net electric field essentially into the electric force equation, and that will give us the electric force. And since we know that the electric force and gravitational force needs to equal each other, then I can guess and check my Q charge, my excess charge needed to float the tape, and that will allow me to figure out what the charge needs to be as long as the forces equal each other. Data and observations. So my length of my tape was 0.199 meters, and using the conversion factor I was able to figure out the mass of the tape, which then I can use to calculate gravitational force. So I calculate gravitational force, and then I use the idea of momentum principle and principle of static equilibrium, since the tape is floating motionless, to figure out that the electric force is the equal and opposite sign of gravitational force. And in my diagram up in the right corner, we see that the magnitudes of the arrows equal each other. Yellow is gravitational force, white is electric force. And it's important to keep in mind that these forces equal each other, which, as mentioned before, allows me to guess my value for Q. So I just kept plugging in different values of Q until my forces equaled each other. And I got that my Q was negative 4.8602 times 10 to the negative 8 coulombs. And this differs by a factor of 10 from my previous calculated Q in Lab 1. So in my code, there's an important difference between the two labs, and that's the way that we're calculating the components for the tape by doing it iteratively. However, there is a similarity between the two, and that's my definition of electric field. So electric field, the way we're calculating it isn't per se different. However, we will be calculating electric field for all of the point charges throughout the tape. So electric field and electric force. So in my code, you can see where I highlighted we're calculating electric field at the location of the smaller charge at the top of the tape due to the small charge at the bottom. And in there, we're using my definition for electric field. And we do this iteratively because the tape is broken down into multiple point charges. And then once we've done that, we're able to use the force equation and plug in this calculated electric field to calculate the force. So here is my diagram, my finished diagram, showing the green arrows for electric fields throughout the length of the tape due to each point charge. And I guessed a charge for Q until the forces equal each other, and here in the bottom we can see my results that electric force and gravitational force do equal each other. In conclusion, this approach is somewhat similar to the use of a point charge in that we use the same electric force equation and we're maintaining the idea of equilibrium. However, the numbers are different for the charge because this model that I'm using takes into account every dq, or every small charge, and therefore takes into account every single electric field that's produced along the length of the tape, rather than just one electric field due to one point charge. So this gives us a more accurate approximation. That's all. Thank you.